So, in this lecture also, that is lecture number 6 of module 2, I will discuss again the 2 and 3 valve conduction mode. Last term or last lecture, like in lecture number 5, I explained about how to calculate the DC output voltage of the circuit when effect of this inductances are taking care, means we are having the U is less than 30 degree. U is less than 60 degree, sorry. So, U is less than 60 degree, and another mode we will see U is more than 60 degree, but right now I am considering this here, this called mode 1, and again I can say 2 and 3 valves conduction is the pattern. So, one state forward that we can go for the 60 degree pulse, the output voltage we saw, and then we can take the average out for that 60 degree, and that will be the DC output voltage. Another way that is a simple as well. Here if you see the conduction pattern here, this is the again if you see here, this is the EB voltage, here EA means your commutation voltage of valve 3 start from this angle 0. Now, I have delayed here this angle alpha, and now you can see once alpha is here coming, then your 2 the valve here, this before that your 1 and 2 were conducting, now 3 is given pulse. So, this 1 and 3 are commutating each other, means the current from 1 is taken care by now 3, means earlier ID was flowing here, now this ID is shifting from here to here, and that period is U period, and in that case the voltage here, because both are conducting, so this voltage is nothing but your EB plus EA by 2 is happening, and that is nothing but it is your minus, you can see EC by 2. So, during that U period the voltage here, output voltage will be this upper part here is minus EC by 2, and the lower is EC because 2 is conducting. So, you can say lower here it is EC, this is your EC I can say, and upper here this for U period it is U is conducting, and once commutation is over, means total current is taken care by the valve 3, this will be off and this will be full fledged conducting, means complete ID will be flowing here, and that is the 2-3 valve conduction. So, this period here, now this is a overlap angle, now you can say the voltage is reduced. So, due to the overlap your output voltage is going to reduce, and finally, you can see this area in every 60 degree, this area is less before that if there is a U is 0. If U is 0, what will happen? This will suddenly follow here and this will come here. So, we are, if U is 0 means always we are getting here for this period this EBC, you can see this will be suddenly going here and this curve will be following, and the EC will be there because 2 is conducting. So, this area A is the shortfall in every 60 degree due to the overlap. So, voltage output voltage is basically reduced due to this overlap. Now, to get this output already we have derived for this case when overlap is 0, and if you remember here I just derived this VD, it is nothing but your VDO cos alpha. Now, what I am going to do, if we can calculate this area, and I will show you this area is very simple to calculate. This area here, it is this curve minus this curve, and we have to integrate from here alpha to alpha plus U degree. So, the area A here, it is nothing but it is your integration from alpha to alpha plus U, and this is your EB minus your EA plus EB by 2, and here it is going to be omega t because this axis is omega t. So, this minus this between this period is your area A. This is nothing but is very simple expression. Here you will find this is your alpha, here alpha plus U, and this is your nothing but EB, sorry, this EB minus EA by 2, and this is d omega t. Now, this is nothing but EBA, and EBA half of the EBA, and EBA is the commutation voltage, and it is our reference. So, I can simply write here it is alpha plus here alpha plus U your EBA by 2, or I can say simply this is a d omega t. Here we are getting alpha plus u under root 3 times this is your line to line voltage, that is your Em by 2 here sine omega t d omega t. And just you integrate it here and put this value, you are going to get this area A, and that is here only for we are talking here 30 degree 60 degree interval. So, this expression here already I have derived, and see from here we got the same expression here, and if you are integrating this sine omega t with respect to omega t, you are going to get cos, and cos here it will be minus of this, and then that is why here the alpha is coming first and this is coming here, means you are going to here this will be minus under root 3 Em by 2 here cosine omega t, and here your alpha plus u will be the limit. So, to put this value, so alpha here this negative will go off. So, we are getting cos alpha here, cos alpha minus cos alpha plus u. So, this is your area A we are getting. Now, since this average is every 60 degree, so to take the average we have to average out for this A is in that what is the difference. So, your this change in the voltage now it is written, it is nothing but 1 over pi by 3 A, because this area was for this we are going to average out for the 60 degree, and again it is repeated. So, this is your pi by 3. So, this is nothing but your 3 upon pi A, and if you are putting this value means now your Vd here will be this Vd minus your change in Vd, and then you can put this value here, you are getting the same expression. Now, you can see here it is the smaller derivation compared to the previous one, because we were getting the two terms separately and then we are putting the value and simplifying it. So, we are getting here again the Vd is equal to your, this is your Vd O by 2 here cos alpha plus cos alpha plus u. You can also from expression you can see if alpha is not 0, what is going to happen, this value is going to reduce, because if alpha is more than this u is more than 0, this value is greater than cos alpha value. So, this is going to reduce if alpha u is more than 0 degree. So, this average is going to reduce. So, the impact of this overlap is reducing your output voltage, and more overlap period, more output voltage reduction. Now, we have to see what will be the pattern of current that is going to taken care by here, because earlier it was ID once 3 was fired, then current is shifting from here to here, and this valve 3 is taking complete current just after the commutation period. So, here it was before this it was ID in the valve 1, and once during the overlap period the current is shifting from 1 to 3 and it is taking completely care. Once this is taking complete ID current here, this will be off, and then we are having 2-3 valve conduction. To here to derive again the what will be the current in the I3 once 3 is going to be fired, then we can write expression. Here again you can write the Kirchhoff's voltage law is a simple in this circuit. This is nothing but from here I can write the whatever the voltage here will be this voltage here as usual. So, here I can write EA minus L di by dt will be equal to EB, and here di is I1, here EB minus L di3 by dt, both will be equal, and here it is written. Means this portion is the voltage corresponding to this, and this portion is corresponding to this. Now, we can simplify all this di by dt in one side, and here is the EBA, and this EBA is nothing but your commutation voltage of valve 3. We also have another expression, that is your I1 plus I3 is the ID all the time. in that period. So, here if you are differentiating, so di1 over dit will be minus di3 by dt, because the differentiation of the DC current will be 0. So, using this relation, if you are putting here, we are getting this expression. Means we are getting expression of I3, I can say it is twice L di3 by dt, and this is nothing but your EBA. So, I can write here from this I3 current, just we can from here I3 we can write the solution of this expression here with some constant A. That constant A depends upon the initial condition that we can determine the A value. So, here from this I can write this value is nothing but under root 3 Em sin omega t. So, now we are going to have under root 3 Em over twice omega L. Now, if I are differentiating here is cos omega t plus A, here it will be minus I. This omega is the integration here, because this is we are going to integrate with the t, not omega t. However, in the DC output we were taking is omega t, because it was the axis was theta. Here it is the time domain, the dt, not d omega t. So, you are getting here this value, and A is your integration constant, and that can be determined that by the putting the initial condition. Means when your omega t was alpha, just it was going to be fired, then at that time your I3 was 0. Means just at that point your I3 was 0 and I1 was having the complete ID current. Just put this value here and you will find this A is nothing but under root 3 Em over twice omega L cos alpha, because here omega t is your alpha. Just put this value, you will get A, because this is 0, and we can have this, and now we can put this value, we are getting the I3 expression here. Means we can write our I3 is nothing but this is a common. So, under root 3 Em by twice omega L, here cos alpha minus cos omega t. This is a one constant, it is in expression it is shown that it is IS2. This is a some again notation IS2, because in the figure again I will show what is IS2. So, this is your I3. Now, we can similarly we can determine I1. I1 is also we can from that expression it is your ID minus I3 will be your I1. Small quantities are basically it is a instantaneous currents. So, your ID is a constant, and I3 if you are going to put it here, you are getting your I1, and that I1 is written here in terms of this. And this expression here I1 or this I3 we are writing only from alpha to your omega t, here alpha plus u degree only, means during your commutation period. Now, here let us see this how the current is behaving during the commutation period u. No doubt this current is rising, it is taking care, it is increasing from 0 value to ID, and this current I1 is decreasing from ID to 0. So, in this interval here we are going to have the characteristic similar to what is happening. This was I can say this was your ID, means it is your I1, and this magnitude was your ID. At once it is going to fired here, it is your alpha degree. Starting from here, let us suppose this is your axis, that we are talking 0, and this is your omega t. So, this current is going to fall, and here let us suppose this is your I3, this is going to take your ID current completely, and this with the period when you are here from alpha plus u period, this is your alpha, this current is going to taken care, and this current will be the 0 at this point. So, the pattern here will be whether it will be, again I said, whether it is going to be decreasing or increasing depending upon whether this current is going to rise here and this is decreasing here, this pattern will follow, or it is vice versa. It is going to increase here and this is going to fall here. To see this, let us draw the diagram for I3 and here your I1. Now, to have this, we can have a axis. This is your big axis omega t. Now, I am drawing the expression. Let us suppose this is a constant. So, this value is constant, means there is some positive value here. I can say it is nothing but is2 cos alpha, because in this I3 this value is added. After that, here minus omega means if it is a positive, then its shape was something means like this. This is a cosine term, but it is the reverse of this minus. So, I can say here this is a cosine like this, because now your axis will be this for this cosine, because this is added here, this curve has shifted. Means if you are drawing only this without adding this, you will have this curve here, but now this is adding this, it is shifted here and now we are having this one. So, this is your basically the expression for here, and this value you will see, although this graph is not so accurate, here it will be like this and this will be also side, it will be the same shape here. At this value, let us see, it is 0 current, because this is we are writing the current axis. So, at this value is 0 and this will be only 0 when this alpha will be equal to your omega t. So, basically this is nothing but this is your alpha, means at alpha what was happening, this was your, let us suppose, ID current which was positive. So, at this value here your ID1 was flowing, means ID1 means your valve 1 current was there. So, this was up to this point your I1 was flowing, and once alpha is given pulse here to the 3. So, this is your ID. Okay. Now, another expression for I1 we can let us see where it is going to happen. So, then here basically this is a curve for your I3. Now, we are going to draw the curve for this. Here this ID is this value. Now, you can see what I am doing. This is ID, means now axis is shifted here and then it is a minus of this. So, we are going to have a characteristic, this is a minus here. So, we are going to have like this a characteristic. This is also cosine. So, what happens, this is the axis is this and now it is inverted, minus I3, because this is a minus. So, this curve will be inverted, but axis will be here because ID is coming, and now this here again it is going to be 0 because this is your I1. This period is your alpha plus u, because this is a characteristic of I1 and this becomes 0, after that it will be off, and then this will be your here and this is your I3. So, this is your basically like this and this is basically like this, it's basically it is not drawn properly and this is a characteristic of this. So, during this period overlap, this is here basically it is declining I1 and the I3 is rising in this fashion. So, during this u period this is a characteristic, before that it was I1 here and after that it is I3, which is again your ID. This can be seen again, which I wrote here, you can see the exact here in this curve. This is the same curve. Now, you can see what I said here, this is your omega t, this is this magnitude is your is2 cos alpha, means here this I3 is negative cosine which is going here. So, this characteristic is is2, means this is your I3 which I draw here. Now, at this point, as I said, it is 0, means here this is your alpha degree, because at alpha I3 was 0. Now, we are having this ID, and this ID plus we are adding this value I2 cos alpha, because what happens here, if we are going to put this value, it is your ID minus is2 cos alpha here minus cos omega t here. So, this minus this is again constant value, and this will be positive. So, this what happens, you can say this is a cosine, but now axis become this, because this ID minus this. So, this has come down below 1 because this is more negative, and this is your I1. Now, at this point when I1 is 0, means this is your commutation is over, and this is your delta degree, and delta is nothing but alpha plus u. So, you can see this characteristic is here, it is just at this shape, and here it is going to this shape, and this is I3 is taken. So, similarly, it is true for all the commutation of the valves, whether it is 1 to 3 or 3 to 5 or here below 4 to here 2 to 4 or 4 to 6 or 6 to 2, it will be in the same pattern. So, this is during this period this shape will be there, otherwise it will be conducting for ID current will be taken care of this one. Now, let us draw the output voltage of the valve when the 2 and 3 valves are conducting, and this is I am going to draw here, this is your line to line voltage, and we have to again to draw this, we have to mark clearly the line to line voltages, or if you are drawing your phase to phase voltage, then this side this phase, this side this, so the difference will be your output voltage. So, again since we are taking our EBA as a reference, so I can write here EBA as this voltage as usual. Once it is EBA, then our next will be here ECB, and another will be your AC. Now, I can write correctly this way. Now, intermediate you can see here, this will be your ECA. Here this will be the reverse of this EAB, and this will be your EBC. See it. Very simple how to write this. I took this EBA. Now, every 20 degree here it is B becomes C and A becomes B. Similarly, at 20 degree here C becomes A and B becomes this. Now, from here you can see this is the reverse of this. So, AC becomes CA. Here you can say this is the reverse of AB. So, it is BA. Similarly, here ECB. So, you can write clearly for all the line to line voltages. Since EBA is the commutation voltage of valve 3, so it can be fired from any degree, here alpha from starting 0 here till here. Now, taking any degree here, let us suppose I have taken very small u, maybe 5 degree, then what happens, now I am taking your alpha here somewhere this value, this is your alpha from here. Now, before that your 1 and 2 were conducting. So, your output voltage was EAC, it was EAC, and EAC was this voltage was EAC. So, up to here this was your output voltage, do not know why it is not going. Now, once valve 3 receives a gate pulse at the alpha degree, now the voltage output voltage now becomes here, as I said, both are conducting. So, this is your minus EC by 2 and this is EC. So, the difference is minus 3 by 2 EC. Now, here we have to see where will be the minus 3 AC by 2. You know these points, all these cross sections, this here, they will correspond to 1.5 of the phase voltages. you can see it. These points have cross sections here. They will correspond to 1.5, that is 3 by 2 of the phase voltages. Now, what will be the phase voltage at that time? That can be taken from somewhere else. You can see here, this is your EB, that is why I said here 0, and this was your EA. This means it is a B, C, and this is your A. You can see just on top here, this is the will be peak will be arising at these points, just corresponding to this. Here also and here also, you can see B will be here. Now, how to know what will be the voltage at that time? It basically depends whatever here you can see what will be this. One thing you can see, it is what is EB, here it will be means EB. Means this value will be 1.5 of EB, its magnitude will be changed, and to remember clearly, this will be your nothing but EB 3 EB by 2. Now, here another point here, what will be this? This is your EB, this is your EC, this is your EA. Here it will be minus EA, here it will be minus EB. Is correctly I am writing? Why? Because it is very clear, you can see this was your, here is EB, and if you are just this is your EB, reverse of this is minus. So, it is minus here, it was your EA, and reverse of this is your minus EA. Now, you will see here it will be 1.5 EA, but with the negative. And another way you can see there is some similarity on the line to line voltage as well. You can see the EA is appearing, this A at the end, means here this here will be your 1.5 EA with the negative sign, because before that you can see it is EBA, A is the minus, and after also it is ECA, means A is there, just we can have a similarity. You can see this is the B, and B was there at first time, so it was positive. Here A and A is there, so minus sign, so it is minus. So, it has a symmetricity. Here you will get C positive 1.5 C, here you will get the minus EB, and so on and so forth. What will be here? It will be minus 1.5 EC, I think it is not legible here. So, this here it will be 1.5 EC here. So, once we are going to fire here, means our voltage suddenly is going to jump here from here, and this will be basically it will be like this, it will follow certain angle, and once commutation is over, now our output voltage will become here, because during this period here it is your period U, here it is your U. Now, means here our valve 3 gets pulse. Again we are going to give the pulse to our valve 4, and that will be here, this is your alpha degree. Now, another alpha will be, this is 60 degree, so alpha will be here somewhere, and where 4 will be getting your pulse. Once 4 is getting pulse, now there is a commutation between 2 and 4 valve, because 4 is in the lower limb, 2 was conducting. So, there is a current change from 2 to 4. Once here it is coming, now what will be the voltage here? So, another pulse here it is getting here, 4th valve is fired. So, it was here, this is conducting, now it is coming up to here, and once you are giving a pulse to 4, now you can see this A, this is C. So, it is here A, EA plus EC by 2, means it is minus EB by 2, because A plus C is your minus EB, and by 2 here it is this, and this was 3 conducting, so EB. So, EB minus minus here means 3 by 2 EB, that is positive, and we have the positive here, as I said it is 3 by 2 EB. So, it will again follow and go up, and now our the here it will be suddenly going to this and it will follow up to u degree, and then this commutation will be over, and then now output voltage will be for your 4 valve conduction. 3 will be your B, here it will be A, and EBA will be the output voltage. Then again after here we are going to get 5th valve, here we are going to get 6th valve, and again here we are 1, here it is your 2, here we are getting again 3. Now similarly you will see if we are going to now at this point we are giving the pulse to valve 5, and now the commutation between 3 and 5 will take place. Once here it is there, now we are getting the output voltage here at this limb, it is your EB plus EC means minus EA by 2. This side the 4 was conducting, so it is your EA, and just here this minus this will be minus 1.5 EA, and again we are getting here this is a minus EB. So you can see this we are, it is a symmetrically we are getting this voltage. So here this will be, it will be conducting here, and once you are getting this, so your output voltage, now this will be your pattern basically, and this will be continuously, it will be the output voltage for, you will find this is your output voltage that will be appearing. So this is the output voltage across this DC link here, and this is a symmetrical pattern, we are getting line to line voltage for the complete 2-3 valve conduction. When 3 are conducting, the voltage is reduced, and once 2 is conducting, the output voltage is higher, and this is the average voltage that we can get as usual. Now similarly we can draw here, once I want to remind you here, this voltages concept must be very clear to draw the exact wave shape of the output. If this you are doing anything mistake here, you will not get, you will get something different output. No doubt here you know the sequence pattern, you know it will be coming, but if there is some fault sometimes, we will see in the inverter operation there is a commutation failure, and at that time you will find it is not symmetrical, and then if you are not knowing the voltage, you cannot draw the output voltage. Here we know that output voltage will come like this, even though you have done something mistake, you can simply say it will be the output voltage. But I will always go for looking these voltages very carefully, even though you are writing this and the voltage here you have written wrong, means you do not know the concept. So that's always I am going very slow, that you should be very careful about to line, you should be very careful about this voltages, because now I am going very slow and you should understand properly. Now we have to see next one, that is for your valve voltage. So now let us draw the valve 3 voltage, and you know from this is the output. Now we can draw on the same here graph what will be the voltage across the valve 3 during complete cycle. So you can see once we get the pulse here, this is alpha because 3 is fired, so this will be your voltage till 3 will be conducting. You can see the 5th is getting here the pulse, means it will be conducting up to this portion till your 5th is getting pulse. Now this is not only up to this point, because due to the commutation. So now the conduction period of valve 3 is exceeding by u degree. Here from this to this point it is 120 degree, because the alpha here we gave the pulse to 3, it started conducting, then it was continuing here up to the 5th, and we are giving the pulse to the valve 5. Now the commutation between 3 and 5 is starting, and it will go up to u degree. So this, and the voltage across once it is conducting, so the voltage across this will be going up to, means this point here. So this is your, it will be the 0 voltage across valve 3. Now here 5th is also conducting and 3 is also conducting. So what is voltage here? Here is a minus EA by 2, here it was EB. No, yeah, here it was. Now what will be the voltage here? Once, even though there is a commutation here, this is conducting, so the voltage across this will be 0. because this is automatically it is going to take it, this is conducting now, this is conducting. So, there is no doubt it will be the 0 once it is conducting as our assumption. So, this is conducting and this is also conducting. So, the voltage will be here, but this across this it will be 0. Now, this is off and fifth is taking care. So, the voltage here is coming your EC. So, here it is EB, means EBC will be the voltage, and let us see where is a EBC here. Your EBC is just reverse of this, means this is your curve. Here you can see we are coming here. This line is your, because the ECB is on top, so EBC will be down one. It's clear, because just it is minus of this. If you are putting here minus, so you are getting the reverse of this. So, this is your ECB. So, your EBC will be this. So, here once we are getting this is off and fifth is only conducting on the upper limb and below is fourth, we are getting this voltage and it will follow. Now, it will follow till 6. So, now we are coming up to this point, here it is coming up to 6 voltage. Now, 6 is going to fire. The 4 was conducting and 6 is getting here. Now, what will be the voltage here? Minus here it is a minus EC by 2. This is conducting. What is voltage here? It is this voltage will appear, and other was your 5. So, the 5 here it was EC and now this. So, we are going to have this minus this voltage, means the voltage across this is minus 1.5 EC, means it is minus 3 by 2 EC during that here the commutation phase, because this is conducting. So, this voltage will appear here and this voltage was already here and this was taking care. So, the voltage here, now we see where is that. As I said, this voltage was your 1.5 EC positive, because this voltage here C is positive, C is positive. So, this will be your 1.5 EC positive, and below here is a minus, and we are going to have this. So, once here it is a conducting, so this will be like this, and means your minus here it will be like this, means suddenly here we are going to have this is going to follow. Now, during the 4 and 6 is conducting only for u degree, this will be this follow and suddenly again it will come back, because this is off and here we are getting your EB again, because this is conducting and EB is again here and this was conducting here. So, for only this u period here it is just going, it is a following, this is a 1.5 minus of 1.5 EC. So, it came here and this commutation is over. So, suddenly it again follow the same. Now, again it will go up to your, let us here this valve 1, now it is going to fire. Now, this 1 is going to fire here. Now, we have to see what will be, and your fifth is conducting. So, now this voltage is going to be minus EB by 2 and this is EB. So, the voltage during that period it is 1.5 EB positive, because this will be EB minus this, it is 1.5, and then we have to see where we are. Now, you can see this is minus. So, this will be positive EB. So, your output voltage, means the voltage which will be appearing here, this your nothing but I can say it is 1.5 EB. So, what happens here, the suddenly it will come here and it will follow up to u degree, and then again it will go back when u is over. Okay. And then it will go up to here this valve 3, let us see, and we will see here what will happen. Means your output voltage you can see it follows here, it is going here this is going here again, here it is coming up with this, and then again it is going till here we are here. Now 2 is now going to be fired here. Now what happens, your this is commutation between 6 and 2 is going to take place. Then again this voltage is going to change. This, what is this voltage? This is EB, this is EC. So, minus EA by 2, and this at before that what was conducting, your 1 is conducting on the limb here 1. So, this is your EA, and you can say it is minus 1.5 EA. Where is this EA? We can find your EA is this much, your EA.
It should follow minus EB in previous.
It will be
in the previous section.
Here we will see the commutation between here, once we are giving the pulse to 1, now there is a commutation between 1 and 5 is taking place, because at that time during this period we saw this voltage across this valve will be your is plus EB 1.5 EB. So, it will follow here. Once commutation is over, now what happens, this 1 is completely taking the current, and this now the voltage across this will be your nothing but EBA, because this is now full phase conducting, and this is your EB, here EA. So, EB minus EA is the output voltage, and it will not go here, it will be coming here finally, and then it will follow till this point. So, this is not correct, it will be coming here, and now we are going to give the valve 2, and let us see what happens. Now, the valve 2 is getting the pulse. So, now the commutation between 6 and 2 will be there. So, the voltage here it will be minus EA by 2, and then it will be here, it will be minus EA by 2, and 1 is conducting here. So, it is minus EA by 2 minus EA, that is minus 1.5, and this is nothing but it is will be your this value. So, your this will be your, it will be coming here, and then it will be up to U period, and then it will be again commutation once it will be over, it will be going there. So, here this is nothing but I can say it is your EBA, and it is going to follow here EBA, and this is going to be here till we are having the 3 is going to be fired. Once 3 is going to be fired, here this will be conducting, and this will be your 0, which will again continue with this. So, your output voltage will be, now you can see from starting from here, once just we are talking the output valve voltage of 3, we are just drawing here. Once 3 is getting pulse, that is a starting from here, we are moving at this here, because 3 is conducting up to here, the 5 is getting pulse, but there is a commutation between 3 and 5, it will be up to U degree, it will be 3 will be also conducting. Once 3 will be off and the 5th will be conducting, the voltage across this will follow EBC, and this will be your output, it will be following this one. Now, at this point, once the 6 is being given pulse, now there is a commutation between your 4 and 6, and your output voltage here is following this. This is nothing but your minus EC 1.5 EC by 2, this is 1.5 EC, then it will follow up to U degree, and again it will follow here till we are getting the pulse to 1. Again, once we are giving the pulse to 1, now the commutation between 1 and 5 is taking place, and now the voltage, because 1 and 5 here, so it is your 1 C, it is a minus here EB by 2, and this is EB, so 1.5 EB, and here we are getting this up to here, and then again commutation is over. So, the voltage again across this is following, 1 is conducting here, and this is B, so EBA, it will follow again here. Now, at this point again we are giving pulse to 2, now the here the commutation of the 6 and 2 is taking place, and then the voltage here it will be minus EA by 2, and this voltage is here, and 1 is conducting here. So, it will be again we are following this voltage. So, now this is output voltage, and again here 3 is fired, means it will be 0 here. So, this is your valve 3 voltage. Now, you can see we are getting one dent here, one rise here, and another here overlap here. So, we are having the certain jumps Whenever there is a two valves are conducting, you will find there is a here dent because it is going in, and this is output voltage here. Again we are following this, here it is here again, and then finally it is here. So, this is valve 3 voltage. Similarly, you can draw the valve voltage for other valves, and you will completely for one cycle you can see. So, here it is a looks very dirty. Now, you can see the valve voltage here. You see here this is the output voltage. Here again we draw this is output voltage across this link. A valve voltage you can see once here is a conducting, you can see there is one dent. Then here this is again overlap, here again this is here, and then finally it is coming 0. So, it is similar to that what we opted. It is for all the valves it will be the same shape, only it will be shifted by 120 degree or so. So, the pattern will be same if it is a symmetrical firing, and we have assumed it is a symmetrical gate pulses are given to the valves. Similarly, you can see the current changeover here from, you can see this is your axis, here we are taking this is axis because the commutation voltage we have taken for this one here, this EBA. So, this is axis here also omega. Now, you can say I3 was there up to u, and then I1 is here up to because alpha we are giving the pulse to 3. So, I1 was ID. Now, there is a commutation between 1 and 3 is taking place. So, here the current is decreasing of I1, I3 is picking up, again it is going. So, this is upper limb current and the lower is the lower limb current. So, it is basically taking care of all the things. So, this is a current. Also, the second graph shows your the upper and lower limb voltages. Here from you can see this is upper and the lower, you can just subtract, you will get these pulses and 6 pulses as well. So, either whether you are going to draw line to line or face to face, means from this face and this side and this side, you can draw only from this minus this will be your output voltage. So, you can clearly draw, and you can also mark the conduction valves when they are going to conduct. So, that is very important in the drawing the output voltage. You have to mark the line voltage, you have to mark the firing angle of the valves when it is going to get the pulse, and then sequentially you can write it, and then you have to find what the voltage will be appearing across. Either if you are drawing the output voltage, you have to see the output voltage. If you are going to see what will the valve voltage, then you have to see what will the valve voltage at that time, and then you have to find that curve, and then you can make it, and it will be symmetrical all the time, you can see. Now, let us, we can relate our output voltage. This is a power electronic circuit. Now, I am going to represent this in terms of your electrical circuit, and we can visualize because we have the electrical equations, the voltage in terms of current, we have the equation, and then we can simplify it. Now, you can see we had this this I3 expression, this was for your from alpha to omega t alpha plus u degree, and this was your ID. Because this ID once you are putting here, as I said, it is your I3, it is under root 3 Em by twice omega L cos alpha minus cos your omega t. This is your I3. You know, once commutation is over, means your omega t is equal to your alpha plus u. Then your current here becomes ID. So, this will becomes your ID, and this angle becomes your alpha plus u degree. Why I want to express this is in electrical circuit? Because the measurement of u is very, very difficult. This alpha is in your control. The current in the limb is in your control, because the some controllers are taking care of the current to maintain in that. So, the DC current is controlled, your alpha is controlled, but this u depends upon your different circuit here, what will be the L, what will be the source here, and this is depends upon this. So, that is not in your control. So, I want to eliminate this u at all, and we can write expression in terms of V and Vd. This is a DC current, and I also want to write in the DC output voltage. So, we have this is a Vd, that is your VDO by 2 cos alpha plus here cos alpha plus u. From these two expressions, we can eliminate this u, means we can eliminate these two terms. And what we can do here from directly we can write what is this value. This value is 3 under root 3 Em by
Pi.
pi. Now, our intention is to eliminate u, means we can directly eliminate alpha plus u. Here we have the alpha plus u directly. So, we can put this side, means I can write this value is your IS2 barabar this, means I can write here this is a minus, this is your plus, this will be equal. Means I can write this cos alpha plus u will be your ID upon IS2 here minus and the cos alpha. Put this value here. If you are putting this value here, means now I can write here V2 by 2, later on we will remove here. This is your cos alpha, and now we are going to put here value, this is a cos alpha inside, and your minus ID by IS2. Okay. Now, what happens, this is a 2 cos alpha. So, I can write here it is your VDO cos alpha minus, now we can just simplify this to this, means it is IS2 here, means we are getting ID is one variable. Now, this is we are having this VDO by 2 IS2, and this is nothing but it is your equal to 3 upon omega 3 upon pi omega L. Just you can see here we are getting this value, and this complete value is represented as RC, and that is called equivalent commutation resistance. This RC arises due to this L value of this winding. This omega L is known as the commutation reactance, and but resistance is 3 upon pi Xc. So, I can write here your RC is, I can write here 3 upon pi omega L, and that is equivalent to 3 over pi Xc. This is equivalent commutation resistance, and here this unit is resistance because omega L is there. So, this is in ohm, this is a commutation reactance. Now, this is your simple, we can represent as a very variable source because your alpha is changing. So, your the VD is changing. If your ID is a constant, your output voltage can be varied only by alpha, or you can vary some of the parameters here, means you can change your magnitude of phase voltage if possible. We will see that is also done in the practice, and here I can draw, this is the equivalent circuit of what we got here in terms of VD. So, your VD is your VDO cos alpha. Why I have written here the variable, because alpha is changing. So, we can change your DC output voltage is changing, minus your the drop due to the commutation reactance resistance here now. So, we can write this your VD in terms of VDO cos alpha minus ID into RC, and here this is expression. So, whole your rectifier, this is a one end rectification circuit. Now, we are talking only rectifier till now, and the rectifier can be replaced by a equivalent electrical circuit. Similarly, we can also do it for your inverter circuit, and then but for that we have to see the inversion operation of this converter circuit. Now, let us see the difference in the converter and inversion operation is not big. It is here the analysis is almost same, only this your advance angle, it means alpha, that is the delay angle is more than 90 degree. So, we have two terms now in the inverter operation which is normally defined. One is called the angle of advance. You know your alpha here, it is your delay angle, normally it is called, and your beta is your called angle of advance. Yeah, advance angle is also true, and it has relation because this your beta is nothing but your pi minus alpha. To see it, let us draw commutation voltage of valve 3, and then it will be more clear what is alpha, what is the gamma, and what is the u that is going to correspond. Here in this axis, this is your omega t. Now this is your EBA. Now this alpha is delayed more than 90 degree. Let us suppose this is your alpha degree, that is delay. So the beta is measured the pi minus this, means your beta here it is your this angle. So the beta is measured from this side to this side. If your beta is increasing, means you are coming here, means alpha is decreasing. Beta increase means alpha decrease, or this increase means beta decrease, because your beta is measured from this angle from 180 degree. Now once the pulse is given here, again there will be commutation, because once here you are giving 3, so there is a commutation between 1 and 3, and it will go up to here, let us suppose u degree. This is your u degree. So this difference is called your here extension angle gamma. So this angle here it is called your extension angle gamma. This angle is very important because this must be maintained some minimum value, otherwise what will happen, if it is exceeding here, there is a possibility the commutation is not successful, because the current here it is I1 is decreasing, I3 is increasing, but the possibility that because the voltage reversal here, again I1 can pick up and I3 can again decrease, so it is a commutation failure. So that's this angle is very important, that is called your this extension angle. So we'll see in the next lecture that how this inverter operation and the voltage of valve etc. will see, and then we'll again model the equivalent circuit of this inverter operation. Then we'll connect by the DC line, and then see whole rectifier and the inverter can be represented by the equivalent electrical circuit, and that will be used for your control algorithms design. So with this, now I can stop here, and next lecture we'll see the complete inverter operation again for the mode 1 when the 2 and 3 valves are conducting. Then we'll go for your mode 3 basically when the 3 and 4 valve will be conducting, and then we'll analyze and we'll see. So with this I should stop, and we'll see in the next lecture about the inversion operation. Okay, thank you.